Okay, thank you very much. And so the first talk was essentially on weather prediction and sort of what advances we have made. Something which is echoing. So the first talk was on weather prediction and how we have made some advances in improving the weather prediction by using AI/ML methods and three-dimensional weather prediction. But today, what I'm going to talk about, what have we done so where do we stand on the next level of prediction is the seasonal prediction. So any of you are familiar with what is seasonal prediction? What is S2S prediction? Seasonal to subseasonal to subseasonal to seasonal prediction. That is called a big term called something called S2S, subseasonal to seasonal prediction. Have you heard about it? Not many of you. Some of you might have heard. So this is where weather prediction is in the time scale of 1 to 10 days. In the extratropics, maybe 1 to 7 days in the tropics. Okay, so this is the time scale of weather. So that predictions, whatever I had talked in the first lecture was for that purpose. And that time scale, what are the phenomena? Phenomena like tropical cyclones or the Rossby waves in the extratropics or lows and depressions. And within them, there are mesoscale systems like thunderstorms and so on, all the extreme events and so on. All that is weather phenomena. And those models were designed to predict them. Now, the next level of predictions are the other phenomena. Like in our system, what is the next? There are subseasonal. Within the season, there are oscillations. There are oscillations known as monsoon intraseasonal oscillations, like MZO, you must have heard. So these have time scales of more than 10 days, but less than 90 days. 90 days is a season, let us say. So that is a period. And then beyond 90 days, more than 3 months average is a season. So that seasonal prediction is for those mean. So that is a climate prediction. So we need that because now, for example, that seasonal prediction is very important. That is we need what we call long-range prediction of monsoon. That is seasonal prediction. Long range means I try to make how much rain will take place over June to September. Mean, total amount. Mean or total amount or mean, sometime in advance, 1 month advance, 2 month advance, maybe one season, 4 months, 6 months advance. I want to know how much mean, what will be my mean monsoon this year. That is what is called seasonal prediction. Or in India, we call it the long range prediction. Because long range means longer than the weather systems, sort of. It has to be more than 10 days. So about a month or 3 months ahead, we try to make that prediction. So those are called seasonal prediction. So we need prediction of these subseasonal oscillations because subseasonal oscillations are very important for modulating our weather. The weather itself gets modulated. When there is subseasonal oscillation, this MJO or monsoon intraseasonal oscillations in active phase, there will be more of these disturbances will take place. So the weather prediction itself depends on this prediction of these. So that is another very important part because that gives me a little, if I can predict these subseasonal oscillations, subseasonal oscillation produces this what we call active and break spells of the monsoon. And if I can predict them more than 2 weeks in advance, then there is a lot of application for that because then the agricultural, the farmers and others can make a proper plan for rowing and sowing and harvesting and all other things. So that prediction is also very much important, more than weather prediction in some sense in our country. So subseasonal prediction, the intraseasonal prediction is a very important part. But intraseasonal, in addition to intraseasonal, I also need to make long-range prediction of seasonal mean. So the seasonal predictions are also very important. So this is a class of predictions which can call a climate prediction rather than weather prediction. So these are different types of prediction. And that requires different systems. Like if we go to longer than weather time scale, in wider time scale, because it is short, the ocean changes slowly, and therefore in 10 days, the ocean does not change very much. So you can assume that that atmosphere alone can produce me the weather prediction. And that is exactly what all those things I have told you in the last class, all those models were just atmospheric models. Atmospheric models will some fixed boundary conditions, the ocean temperatures are given, and then you make the prediction. So ocean temperatures have been fixed. There is a little bit of error in that, and still it gives you reasonably good forecast. But when I go to sub-seasonal forecast, the intra-seasonal, which time scales are about 40 days, and seasonal mean, which has time scales of sort of 90 days. So then I cannot neglect the ocean. Ocean and atmosphere interact very effectively to create the mean. And therefore, if I fix the ocean boundary and try to use the atmosphere, it will make error. Because it will not, because as it evolves for 30 days, the ocean has changed the atmosphere significantly. So therefore, your average will be wrong if I don't have the interaction. So it is a must that when you go to S2S prediction, that is subseasonal to, we have to go to a coupled ocean atmosphere model. And that is what most of the climate models, the seasonal prediction models are that kind of a ocean atmosphere coupled model. So there is a whole need of separate class of models are required, and which is normally being done with our NWP system. Now, to go to our data-driven system also today, we have to go to this kind of a system. We have to emulate such an ocean atmosphere coupled system. And that is why this is a different class of problems. This is not the same class of problem. So therefore, what I'm going to do today is just to give you, because this is a more complex problem, and the advances are lagging behind what has been done in the weather prediction, because there is only atmosphere model. And so what I'm going to do, and still it is evolving, but evolving faster. So what I'm going to do is to give you a sort of status of where do we stand in terms of, in this direction of building S2S models, building data-driven S2S model. And then I'm going to say that in this case, for the climate prediction, you can, instead of going directly into a three-dimensional ocean atmosphere model, you may be able to build somewhat simpler models to address certain specific questions. And that is what we have done, to try to do some simpler models and to address some specific questions related to monsoon. And I'll give you one or two examples of that. Okay. So, because the next problem is a little bit more complex, and that is still requires more computational efforts and more data and so on. I'll give you the challenges that we have. So let us start with what is the S2S problem. So in the seasonal prediction problem, the El Nino and Southern Oscillation is the ENSO you must have heard. How many of you have heard about ENSO? How many of you understand the phenomenon? How is it? How it dynamics of ENSO as an coupled ocean atmosphere phenomenon? Okay, good. That is so. The prediction of ENSO is therefore very, very important. That is because this is one of the largest inter-annual signal in the whole world globally. And so therefore, this is the biggest inter-annual signal. And therefore, since the signal is large and it is coupled, we expect that there will be a large predictability. And people have studied and we know that there is predictability. So these coupled ocean atmosphere models are now trying to predict that. And what is the status? This is the kind of status that this is the status of our coupled ocean atmosphere models. So this is a set of a correlation, sort of the skill or the status of what the prediction will be. This is from a bunch of models. Sometimes January, February, March. This was initialized by a whole class of coupled models, and they made predictions of this year's El Nino. Right now, there is an El Nino, there is no El Nino. Right now it's sort of this is the kind of conditions, the current condition. I actually took this that I was downloaded yesterday from some this observing. There is a network from which the real-time data actually comes these days, and this you can actually see what is happening. And this is PEML करके the Pacific Environmental Research Laboratory in Colorado. They are custodian of this, and they are this global observing network data comes there. They analyze, put it in a portal, and you can actually view it in almost real time. This is really great thing today. And so from that we know that this is the anomaly of sea surface temperature, and this is almost close to zero, just a little bit of positive, but it is close to sort of more or less normal condition. And these prediction systems, there are a lot of different models predict differently. This is a zero anomaly averaged over some box here, over a box in this region, equatorial box called Nino 3.4. That box average predictions are close to zero around, we are now June, July, August, right? This is a close to zero, but there is a big spread. So many models predict somewhat higher values, many models predict somewhat lower values. So, but on the ensemble mean of all these predictions are close to zero, and that is exactly what's the kind of, so models are now able to about 6-8 months ahead we can predict, but so that has evolved. That is the kind of the dynamical model skill is improving, but there are still a lot of limitations, and it turns out that the ENSO has a lot of diversity and a lot of event-to-event variability, and we cannot do that. And when the initiation, when the ENSO will initiate, we may not. We are not able to predict that well. So there are issues. All these are kind of challenges still remaining in the dynamical models. So when you come to similar things for monsoon, our problem is even worse. And so we can do reasonably well. In fact, up to about 8-9 months ahead of time, we can predict reasonably well. But in monsoon, I cannot even predict more than the mean monsoon. June, July, August, September rainfall over India, I cannot predict even more than 1 to 3 months ahead of time. And there is still, the skill is still very poor. So these are the challenges in our seasonal predictions, especially for monsoon. And so, this is where we expect that the IML will help. And there is definitely a great potential for improving these seasonal predictions, especially for monsoon, globally also. Once we can go to a three-dimensional emulators like the prediction problems in the weather case, and that definitely going to be, even without going to such an emulator, I believe that we will be able to improve the seasonal prediction of monsoon far better than we can do by the dynamical models today, and I'll demonstrate that in this talk in a minute. So there are a lot of challenges though for doing seasonal prediction by these huge challenges. One big challenge is the difference between the data requirement becomes very large. Can you think of why? Can any of you think about how the data has been used for weather prediction? And now I go to prediction of the mean of 3 months, 3 months mean, June, July, August, September mean, or December, January, February mean. I want to predict. When I do weather, I want to predict today, tomorrow, or day after tomorrow up to 10 days. But this can happen throughout the year, any time of the year, because I have to keep predicting the weather anytime, right? And therefore, there are your hourly data for 24 hours a day, 365 days, and there are 40 to 50 or 100 years of reanalysis data is there. So we have a lot of combination to train the data on daily time scale or hourly time scales. Right now, I have to train the data with all the combinations of 1 hour forecast. So I'm making 1 hour forecast, right? So I want to find the relationship between 1 hour forecast and the next T minus 1 hour forecast. And then what is the relationship? And based on that relationship, what will be T plus 1 forecast? So this relationship, there are a lot of combinations now I have. And that combinations can give me good training. And that is why weather forecast has worked suddenly. And that is, I mentioned that in the last talk also, but this is what more. Now come to prediction of seasonal mean of June, July, August, September, June, July, August mean or December, January, February. That is for 1 year, that's one data only. What do I do? That means if I have 100 years of observation, 150 years of observation, I have only 150 years of data, 150 members, right? So then I have not enough to, and so therefore, and this, there are a lot of variations will be there. And so as a result, there is very little data from observations. Now, how do we cannot simply go ahead. But there is a possibility that with what you call the climate coupled model intercomparison project called CMIP has now simulated data. So these are not observations, but simulations. Simulations under the same physical conditions, same physical forcing over the historical period. Again, 150 years of simulations or that. They are surrogate observations in a way. There will be biases, but they are also like observations. So if I have many such model simulations, I can use the model simulations as to train for the same seasonal mean, whatever seasonal mean that we are having. I'll give an example of that little bit. So that gives our opportunity, some opportunity. Of course, it is not the perfect, because observationally we are never going to have enough data. We have to train on model simulation. That is why models are important part of this, although they have limitations in predicting. But training, they will be very, very useful. And that is what will have to be, that will be the only way that we will be able to train. Or generate some surrogate observations in some other way. So there will be, these are the things that are going to happen in terms of training. So that is why there are a lot of challenges, because there is the number, to have adequate number of observations to train seasonal mean, you require many. So we have something like, I have given an example of like 45 models with about 10 member ensembles of simulations of 150 years. Then you will have that many, and that may be somewhere in the ballpark of feasibility for training. So this is the kind of things we will have talked about, but so what is the status? Obviously, as a result of this is lagging behind. But as far as I know, right now we still don't have we haven't come out, just like that landmark study by Lam et al., and then followed by so many other developments of all the three-dimensional atmospheric models. Though like that, we don't have a three-dimensional neural network model for ocean atmosphere, coupled ocean atmosphere model. We don't have right now. But I think that within next 5 years, it will happen. And then going beyond that, it will be, more improvements will take place. But before going that, before all this thing happened, about four years ago, 2019, a paper appeared on predicting the El Nino itself, only El Nino. Let us not making a global seasonal prediction. I want to predict only El Nino. So I take an index of El Nino. I predict it by using some, and they did a very good by using AIML method. This is a paper published in somewhere, I'll show you in a minute. And that actually triggered us also, started thinking about that. Was even before the weather prediction models came out. So in fact, that paper by Ham et al., I'll mention it in a while, that actually sort of excited me to get into this problem of how, and I recognize that this is going to be a very, very important part coming in coming years. So I think that the outlook is that in about next few years, 3D Earth system model, data-driven 3D Earth system models is going to come. Again, it will be based on training from CMF6 models, but still it is not a reality. And I'll give you a couple of examples where we are happening at this point. So before going that, let me show you this example. This is the paper I mentioned. So this was published in 2019 by somebody called Ham et al. So this is about 5-6 years now, 5 years. So this is a very simple model. So you're not solving the 3-dimensional problem. So only using 2-dimensional neural network, a CNN model, and trained on SST field and the heat content field. So the ocean has the 2-dimensional heat content field and heat content anomalies of sea surface temperature and heat content anomalies and heat content anomalies. They use them as predictors and found the relationship between the predictant. The predictant is in the index of El Nino. That is the sea surface temperature average over one of those Nino 3.4, which is in the Eastern Pacific equatorial region. There is a box, and the box average monthly mean temperatures, they try to predict it. And for that, they developed models based on how that the sea surface temperature anomaly averaged over 3.4 is related to the patterns of SST anomalies and D20 anomalies over the whole globe. So that patterns then are used as predictors, and very simply. So and then they were able to show that that this is their prediction skill. This is a skill now. It is not anomalies. The correlation coefficient between actual predictions and observations, actual observations. And these are as the lead time goes, this is a lead time of forecast. 1 month ahead, 2 months ahead, 10 months ahead, 12 months ahead, 18 months ahead of time. That Nino 3.4 SST anomaly is being predicted by the model so many months ahead of time. And that is the dynamical models can go up to about 0.5 correlation, as I said, is kind of useful. Not below that, it is not useful. And above that, it is better. So if we say that this is the limit on our predictability, so the dynamical models are able to do up to about 9-10 months, but this model can do all the way up to about 18 months. So they showed that, but by using just like see before just like the weather prediction models, this model was able to extend the lead time of forecast several months ahead, better than the dynamical models, best of the dynamical models. So even using a very simple model. So I was quite excited about it, and that is how I started learning a little bit about AI/ML methods, and I learned from Adway about what goes inside these, and so I'm still learning. I still don't know what actually goes in, but I know what is the kind of principle they use, and that is what I'm going to try to apply. So this happened, but this is still a very, very simplified model. It is not a 3-dimensional model, but in the 3-dimensional sense, it is still we are not having much success. And this is a method. This is a model which has recently come, not even published. It is still in archive. This is by a Japanese group. I know Toshio Yamagata. He is a friend in our IOD paper. He was a co-author. So they have developed an ocean emulator. And this ocean emulator is something similar to, think about it, the same thing is like the weather prediction models. Now they have tried to do 3-dimensional ocean, but the ocean has to be, if it is ocean, it has to be forced by winds. So the winds are forcing the ocean and producing all this. So therefore there is a problem. If you want to put it in the forecast mode, then you need data, so you need forecasted winds. So you have to use the forecasted winds to make those. So there are issues like that, but still it is an attempt to see, given the winds, can I make predictions of SST by using properly? So they use that, and so developed a model I'm not going to technique again, but so this is something that is demonstrated that they can also, they can also make predictions better than the dynamical models of the ocean. By using ocean itself, they can make predictions up to about 18 months lead time. So this is something similar to HAM, but now using an ocean model, a proper ocean model. They did not use any model. They use simply data. So the second, but there are issues. This model still has a lot of issues that's still to be resolved, but it shows some feasibility of doing it. So the next thing that has come out very recently, but it has not still published, but last year, middle of last year, they had put it in the archive. It is still in the archive somewhere. I think it has not been accepted for publication because this also has some problem. But this is a more ambitious. So this is a coupled ocean atmosphere machine learning model. So now used in the ocean model, three-dimensional ocean model, which has several layers. You use atmosphere with several layers, and then you use a coupler also. Somebody talked about coupler yesterday, right? So you need a coupler between. They use that. And this is also coming from NVIDIA mainly. So these are some Indian, Jaideep Pathak is there, he has been there probably. So they have used that spherical Fourier neural operator architecture, and atmosphere is trained on ERA5 data, ocean is trained from some ocean analysis data, and then they have certain strategy. But they showed that they can make some up to about 3 months forecast, the couple model. But after 3 months, the model doesn't work because it blows up or something, some problem is there. So it still has a major problem. So these are the kind of, we are in that stage. It is still on a very preliminary developing stage of ocean atmosphere couple models and in the data-driven ocean atmosphere couple models. So this is the state of affairs. So they showed that okay, if up to 6 months ahead we can make good forecast. They can also they showed that the ocean subsurface temperature anomalies are quite realistic, like what is observed. So all that they showed, but they cannot run it. It still has problems. So there are some issues, and we need to solve all those technical issues and not non-trivial issues. So now where do you stay? Let me now get back to monsoon, because that is our more interesting. So finally, as a nation in India, what is our goal? Our goal should be goal of predicting the monsoon better.
So in that ocean model, right? Do they get the boundary currents and all right?
I won't be able to. I have not checked that in that details. I think I have given this. You can look it up. This reference. I will share these slides to everybody, so you can have a look at it. But I have not looked at that. I did not even go into great details. It is just to tell you this is the state, and I did not even examine why they are failed or not failed. I think you are talking about the other one, no? This one, yeah, the reference is there. So as I said, it is not yet published, but this is really evolving very fast, and many of these are actually you have to keep looking. And I'm not that good at looking at all the literature. Maybe I have missed some literature, but that is what the status seems to be today. So I want to concentrate on something that. But as I said, so our interest in doing a coupled ocean atmosphere 3-dimensional model is also to get better prediction of monsoon, because today the simulation of prediction of monsoon by dynamical model is at a very bad state. It is not great, and this is the state. So if I take a whole set of operational forecasting models which are making forecast of monsoon, and I look at their skill, what do I see? I see that at 1 month lead, we have about 0.5 skill. And we in India have done a little better than that by using our own models at IITM. We have gone up to about 0.65 skill. But if you take many different models, ensemble mean is still remains about 0.5 only. Okay, there are many models which do very poorly. But you have to see, one model is not good enough to make prediction. We have to have, because models themselves have their own little bit of, so we need an ensemble of model. And we have not seen ensemble of models which are able to give us now better than 0.5 skill. So that is not very great for us. So we need to have a better skill. Secondly, we need to also have be able to predict it more than 1 month in advance, 3 months in advance, because now these models cannot make more than 1 month. It cannot make any useful skill at all. By 3 months, it is just gone. Models cannot make any skill, meaningful prediction. So the seasonal prediction of monsoon is in a terrible state globally, the dynamical model, and it is not going to improve because of the error growth problem that I mentioned in the first talk. Same problem is going to limit our seasonal prediction skill also, because they will grow, affect the the small scale errors growth, affect the large scale error growth. The large scale error growth affects the mean, and that mean is also going to be limited because of the errors in the initial condition or errors in the model, both. But models also, all these large scale models, prediction models have large model errors. Those model errors keep building up. So these two things are not going to let us improve this. And so therefore, that is where these data-driven models have a great potential of improving this. And we have demonstrated that by a simple model. So this is a model that we have developed, but there are two papers that is related to it, and it is my student Devavrat who has done most of it, but in collaboration with Adway and Bipin and in their group. But before going to actually prediction, I cannot go blindly, because unless I have to know that there is predictability at long leads. So far, nowhere in the world, nobody has established the predictability of monsoon rainfall at lead more than 1 month ahead. Simultaneously, people have done some work, and we know that monsoon should be predictable, has high predictability simultaneously, short range, short lead. But at long lead, we don't know. Maybe there is no predictability. If there is no predictability, there is no point in trying with data-driven model. Then I will not have any trust on them, because you have to have predictability. Is it possible to predict at all if I have a good model? So that predictability study first we did. So we did, this is a paper published in QGRMS. Here we showed that the efforts in prediction as well as predictability so far has been flawed, because everybody has been used sea surface temperature as the predictor. And because sea surface temperature is what has the memory, that is, it connects with the atmosphere and it affects the convection and all that. And so it was good to think that sea surface temperature is predictor. But sea surface temperature as a predictor also, people have been using wrongly a index of the El Nino index of Pacific only. Now this has been also so we realize that has been a mistake. Why? Because when you do correlation between sea surface temperature on the Pacific with ISMR or the monsoon rainfall, you are only finding only a partial relationship, because ISMR is affected not simply anytime. Anytime ISMR is affected not by only Pacific SST, but also SST around the whole globe. Because in Indian Ocean there will be IOD, in Atlantic there is this Atlantic Nino, all these also affect the all the water circulation. There are these three water circulation. This water circulation exact location and strength is determined not simply by the Pacific Ocean SST. Even though it is strong, there are small things here and there also will have a little tweaking and that will have an error. So that the actual thing, actual SST, so it has been a big mistake, because that is why we are not getting the estimate of correct potential predictability by using the SST. We are assuming that, okay, this much only should come, and whether we are not even looking at those things, using that as a predictor at long lead. So there has been a huge gap in our understanding in that. And so here what we said, that the first thing we have to do, you have to have a predictor which will include, whether it is the SST variable or any other variable, contribution from all the basins simultaneously. It must have. Then only that predictor will be able to assess the potential predictability. And so we showed that NINO3 may be a good index for ENSO itself, but it's not a good index for monsoon prediction or any other regional prediction. Any other regions, if somebody wants to Australian rainfall or African rainfall, they cannot do simply by El Nino. They should take all the others, other basin data. So with that, we devised a new methodology to identify new predictors and then use that for prediction. And this is the paper which identified a new predictor, and the two predictors we identified. One is something called SP or sorry. Okay, so what we did, we tried to find. So we defined new predictors. One as actually three predictors. One SST-based predictor is called SNINO. This is called I call them. These are all we call them global NINO. We just don't call NINO. NINO is essentially Pacific-based. Most of the so we have to have a global NINO index. And what is the global NINO index? Which will use all the, including Pacific. Pacific is a dominant driver, no doubt, but it is not the only driver. And if I take only Pacific, then I will miss out with some contribution, and that miss out contribution will affect my prediction skill. So that is so one SST predictor called SP or SNINO, and D20 is the 20-degree isotherm. You know anybody? I mean, of course, oceanographers will know, but any of you know what is D20? You don't know? D20, so D20 is the depth of the 20-degree isotherm. If you plot the with depth with the SST values, suppose this is like the equator, around equator. This is 100 and so 60-degree east to 90-degree west. It is from Indian Ocean to Pacific. If you go to depth, the Pacific, the thermocline will look like this. It will depend here, and then it will go down, and then in and sort of in Indian region, it actually will. Again, in the Western Indian Ocean, it will be shallower. But in the Eastern Indian Ocean, it will be again deeper, because this is the part of the warm pool. So this is the kind of, about, suppose I take the 20-degree isotherm, 20-degree isotherm, it will look something like that. So the depth of the 20-degree isotherm is a measure of for the warm water volume, warm water above the. So this is more of a mixed layer, and this is temperatures are not changing very much here, and then after that the temperature starts changing more rapidly. So therefore the upper layer heat content is the 20-degree isotherm gives a measure of upper layer heat content. I can use heat content by different method, but this also is one way of doing it. And this is important because of the it is close to the thermocline. So all the ocean can be tropical ocean, can be seen as like a two-layer system. one layer above the thermocline and one layer below the thermocline. So all the other big oceanic processes, the big waves, the coupled waves, is just manifest in the variation of the thermocline, variation of the 20-degree thermocline, isotherm. So that is why 20-degree isotherm is a very good measure of the oceanic, slow oceanic variation. And other point is that because the SST on the first SST is here, but but D20 is here. So what happens? SST is in touch with atmosphere, and atmospheric heat fluxes affect the SST. So even though dynamics affect the SST, ocean dynamics, but atmosphere also affects it. So through the atmosphere, SST gets a lot of high frequency stochastic noise. And that leads to a stochastic high frequency variability, which leads to a stochastic noise on the mean. Mean SST will have some stochastic noise coming from high frequency component of the atmosphere. D20, no problem, it cannot, because D20 that does not penetrate. So D20 isolates any high frequency stochastic noise from the atmosphere. That is why D20 becomes a better predictor. And so, and then we had another and the heat content based predictor. So all these three predictors, what we did, we devised the predictor by, now we first look at the correlation map of correlation map of Indian monsoon rainfall with the D20. So we have a map which will give you something like an El Nino ENSO signal, but also there are contributions from the other basins, and then a different lead, this correlation will be different, and this at each lead I take the correlation map as my basis, and I say that what is the contribution for every month, how my D20 anomalies are projected into this correlation. The hypothesis is that if wherever the correlation is high, if the D20 anomalies coincide there with high values, then it will have stronger impact. On the other hand, if they are mismatched, it will have a lower impact. So the projection of the D20 anomalies on every month on the correlation map gives me an idea of how I can integrate the contribution globally from all the basins into one number. And that is what worked. And so this way we divided this, and then when you do that, and estimate the correlation with the monsoon rainfall at different lead times, it turns out that the D20 based predictor has the highest correlation. So this is what I call potential predictability. And the potential predictability with lead time actually is very high, remains except for some dips here. Due to some dynamics, there are issues because of phase locking with the annual cycle. There will be some dip, but there are all these regions, see, very high predictability exists. And this was not known before. And now we have a physical basis also for that. Then another thing that we see is that, but interestingly, now if I take the SST predictor even at 1 month lead is much poorer than the D20 predictor, and because of the stochastic noise, as the lead goes up, it doesn't produce. Same way I have constructed the SST. All three basin contributions are there. Still, it is not able to predict better. So that is because of the inbuilt stochastic noise that SST. So we have been doing it wrong all the time. Now this is a predictor that we can now trust and use them to predict. So D20 is a better predictor, and if I do the sort of moving correlation, it turns out that even in the recent time, the correlation can be as high as 0.8, 0.85, and so on. So, and the D20, of course, these are not like NINO 3.4. NINO 3.4 has this multi-decadal variability. This is essentially due to some sampling noise, and then but this nothing is not the multi-decadal variability of this also is very less. in D20. So all these are makes it D20 a much better predictor, not only for estimating the potential predictive, but also actually making prediction. And in the next model, so we developed a simple CNN model, something similar to what Ham et al. Did for ENSO. And so we train by using a whole set of 45 ensemble members simulations from 17 CMIP6 models and train them by using something called a physics guided training process. Now this physics guided training is very important because when you go to high lead time, you cannot simply ask the model to train itself with all the relationship at different leads or lags, right? So that is why we decided to do that hierarchical aggregation, temporal aggregation method, and develop one model for each lead forecast. And so why do you do that? That is because see, so when you do it for each lead forecast, if I look at the correlation map between the ISMR and the D20, it is related to this ENSO, global ENSO. Global ENSO is evolving, and the evolving global ENSO had different phases. Different phases or different lead times, different combination of the Pacific, Indian, and Atlantic basin contribute to this. And we are able to take that. So now, instead of, suppose I take only, so for one lead 1 month, so I take only one, the data with one month lead, 1 month lag, and so, and then train on them. I don't take all the data. So, and then 2 month lag, I only 2 month lag data I take and train on them. So like that, I am forcing, physically guiding the model to see what is the dominant pattern, dominant relationship. If I left it for it to train, it will not be able to. Now it is very easy for the pattern without being very complex network. I can actually find a very good, because dominant pattern is there. And now only because it is non-linear, it is a non-linear pattern recognition, it will do a better job than my doing simply UF or something. And that is what it is. The simple method, but if I guide it towards the dominant mode of variability, dominant, then it will work. And that is what happened. And every lead I do that separately, therefore it works. And so, and that leads to my skill, which is now is kind of quite impressive. Now you see the dynamical model skill goes down, but our skill, consistent with my predictability studies, it increases, because in the higher skill and consistent with predictability studies, at some lead of 7-8 months, there is a dip, and then there is this actual skill. These are actual skill. So we have designed the model, some parts for training, some parts for verification, some parts for testing, and so on, and all that independent data. After that, it turns out that there is, at 18-month lead, we have a much higher skill, which is quite very impressive. So, but for 2 years, we have been having great difficulty publishing this paper, because because the reviewers thinks that, well, we must be doing something wrong, because they think that is impossible. Well, nobody is able to understand, first of all, the basis for predictability. And secondly, we're saying that I'm giving you the code, you test it. They are not interested in testing it. They're saying, no, you explain why, how can it be? Models are not able to predict. Of course, models are not going to predict, because there is a error growth problem. I don't have the error growth problem. I have overcome the error growth problem by doing this hierarchical aggregation method. Simply, there is no error growth there. For I should get the potential predictability. I do get it, but still this is I think this is a bias from the Western reviewers. Even the Indians, they don't understand. So as a result, we have a huge problem. It's still going under review in QGRMS. I hope now it will get published, but we had great problems. So, but I think this indicates, this is an example that if you must have any applications. First, you have to see what is the basis for predictability. Predictability. First, you have to see the predictability. Without looking at predictability, don't blindly apply. If you see that there is predictability, then go ahead and design the model. And when you design the model, try to guide it to get the dominant dominant relationship, which we see from linear correlation. Linear correlation only gives me what is dominant relationship, but that is not correct, because actually relationship non-linear. What is a non-linear part of that relationship will now your AI model, the machine learning model will improve on that by finding what is the non-linear relationship, dominant non-linear relation. It's like a non-linear regression. It will find out. So that gives you the best correlation. So I think that is the message that we get from these. So we are now able to apply that to this. What is the time? We are already late. 5 minutes? Okay. So I'll not go. Then I'll just come to the last. So we have applied this. So I have lot of other things. Then we have now physically been able to explain why this works. After a lot of thinking and how to present this to the people, the reviewers, and the general public. So I think we have a better way of explaining it, how this large the global connection affects the local moisture convergence into the monsoon region. The interaction of all these water circulations finally leads to strengthening or weakening the monsoon through this the moisture convergence due to the local Hadley circulation in this region, and that I think we are hopefully will convince the people. And I think, so now we have applied it to another problem. Devabrot has applied it to another problem of prediction of extreme rainfall frequency. Okay, I'll not go into great details. I have to skip because I want to show you something that we have done, and Bipin is involved with that here. So this problem. So now we have applied it to something, and this is Bipin's work. Bipin is right here. So we have able to develop a simple model of climate variability in some sense by using only SST. So we cannot develop a three-dimensional model because of our resources and all that. But we have to also, before even going that, we have to need to try this. And so we tried this first. A very simple model. Take the SST data only. Ask the question. Now my all these CMIP6 models, these global models, simulate this SST through ocean-atmosphere interaction because the coupled ocean-atmosphere model. Now SST itself is a result of ocean-atmosphere interaction. So if I have the SST variability, I can simulate correctly. I have a model which will simulate the SST variability better than the CMIP6 models, because CMIP6 models have their own biases, and because of that bias, I am having error in my ENSO predictions because in the seasonal prediction of ENSO. And so suppose I can avoid those bias and develop a model which will simulate the SST variability better than this and closer to the observations, then that kind of a model will be is a much better seasonal prediction model for El Nino. And so that was the goal. To do that, we used a simple all the SST data from a large number of so this is the philosophy that I have already told you. So so large number of CMIP6 models, and I trained them on that, and then fine-tune it with observed SST. Observed SST only one sample, right? So there are some 2-3 different SST analysis. So we take one of the best analysis and then fine-tune the model with the observed, and then use the model to simulate monthly SST anomalies all the way up to 1,000 years. so that it is able to, statistics of the variability, it is able to simulate correctly. And that is our goal. And what is the variability? What do we want to simulate? We want to simulate the global pattern of SST variability correctly. And what is that global pattern? To demonstrate that, we have used a UF of the global SST anomalies. If I do monthly mean SST anomalies globally, and then you have got 3 UF determines 3 different kind of measure modes of variability. And I want my model to simulate these modes correctly. That will be my test. In the verification, I am not going to do point by point, but I am going to look at how the model is simulating the variability. Variability means these 3 different modes. So from observations, these modes represent, the first mode represents an El Nino kind of variation. It's a 2 to 7 year periodicity, but nothing much, no decadal, nothing. So this is the dominant ENSO, global ENSO mode. Okay. The second EOF represents some sort of a multi-decadal variability. So ENSO has also a multi-decadal component. So this is a ENSO multi-decadal variability. So the third is more of a ENSO. It is also multi-decadal. So this is actually ENSO multi-decadal. This is more of a global multi-decadal variability. It should have had some so specific decadal oscillation is there. So it's more related to the Pacific decadal and AMO combination of that. So this is the kind of, so this is more of a multi-decadal oscillation. This also dominated by ENSO, but has a little bit of modulation by the multi-decadal part. So these kind of 3 are from whatever data that we have. Remember, the observed data is only 150 years. So the multi-decadal part cannot be resolved very well. And that is a big problem. So then when we did this, so you have I don't want to go into details of the model. And in fact, we had a lot of difficulty in the beginning. And finally, finally, Bipin found some ways of generating first generate the annual cycle, and then build a model which to simulate the anomalies. So it's a sort of 2-step process. In that 2-step process, also we had initially did not know how to fine-tune your observation so that we don't lose the memory of the training from the CMIP6 model. So this is a kind of lot of good amount of research has gone on that. And finally, when we did was able to do that, that it had a lot of improvements. So think about this. So first we looked at, let us say, the standard deviation of, this is the observed standard deviation of monthly anomalies. So from year to year. So to take all the monthly anomalies and year to year standard deviation, if you do, so you of course have El Nino signal here, but there is also large month-to-month variability in the extratropic. But the models, these are 3 different models. Okay, these models produce too much of monthly variability. So if you have these models and then try to make prediction, seasonal prediction, you will have a lot of errors because it is overestimates the month-to-month variations. A lot of noise will be there. And so your predictions will be messed up completely. So we need to get it down. And so when we did use this new simulation, when I do, so new simulation when I do with fine-tuned with observation, it comes out much closer to what is observed. So that means now we are pretty close to simulating the month-to-month variability almost globally. So that is one good thing. Second thing is in terms of the improving the modes of simulating the modes of variability. So this I'll just stop with this one example. These results are when I don't fine-tune with observation. So he simulates this, he uses the CMIP6 simulations to train and then develop the model, let the model run for 1,000 years, and I look at the variability without fine-tuning with observations. When fine-tuning with observation, you have to sort of retrain, readjust, optimize your parameters. So that without doing that, if I do that, what you do, the model, the actual model, when trained on SIMF6, still is very poor because it does not produce the dominant mode as the answer mode. The model has its bias such that the dominant mode is not answer mode, so it will not produce answer predictions well at all. So, and the second mode comes, and so has comes as a 7 mode, is variance is only 7%, and something spurious has come, which is a very strong variability. So this is what messes up the actual. So simply by training with a SIMF6 model, I won't be able to do a good job. When we fine-tune with observations, however, now the answer mode comes on the top. So this is fine-tuned data. Now it is the answer mode is the dominant with almost 20% of the variance, which is close to the observation, and more or less the second and the third mode also are closer to the observations. So that means now total variability is much closer to the observation. Therefore, I can expect that this model will make a much better prediction of, I can now use this model as a seasonal prediction of ENSO, and we are going to test that anyway, and see whether it does better than dynamical models or the Hair-Metal model. Or at least comparable to Hair-Metal model. So I'm sure it will be better than Hair-Metal model if I do, I think. So this is, so it is in a way, I think this is I feel, maybe in the again Westerners will not agree, but I feel that this is also a small landmark in terms of being able to develop a climate variability. But most important thing is that the biggest improvement, I mean biggest satisfaction is that this is a rollout model, okay? So he makes 1 month forecast. So use that forecast as initial conditions and then make what will be the next month's forecast. So how does it made? So now the new forecast is a different pattern. Now at t equal to 0, now that pattern, how is it related to the previous pattern? 1 month before that. So that we have trained the model to look at given any pattern at t equal to 0 and t equal to -1, what will be my t plus 1? That has been trained. Now that training now give me, my pattern changes little bit, what will be my next pattern? And it is giving me that. And it is giving me so that I'm not losing the memory of the El Nino evolution. It is coming so that it is giving small changes, is giving another change, another change is giving another change, and all that is still retaining the answer so well. And that means that is a big achievement in terms of training, because without a good training, it will not happen. It will then it'll decay or change into something else. So it hasn't happened for 1,000 years. I think this is a great achievement. So I think it has potential, and it can now go for this 2-dimensional to 3-dimensional, and then maybe you can have an emulator for couple model based on this. So with that, I'll stop. Thank you. I think I have taken more than.
So thanks a lot, Professor Goswami, for yet another extremely insightful lecture. So floor is open to a couple of quick questions. Yes.
Hello, sir. So I have a question. When you mentioned that there are 3 predictors, SST, D20, and HC heat content for the ISMR. So do they take into consideration the northward propagation of ITCC that brings interseasonal variability?
No. No dynamics like that. So here it is all data driven. So basically we are looking at the pattern of SST or D20 or heat content, and pattern of anomalies of D20 heat content or SST, how it is related to, just it is relationship related to ISMR. So the ISMR and D20 in globally has a pattern of correlation, relationship. So that pattern is what we are looking for. That means at everywhere, what does that mean? Correlation pattern means that, okay, if there is a SST anomalies or D20 anomalies in this region, it has a stronger correlation. It means that whenever there is more D20, ISMR tends to be higher, stronger, and so on and so forth. Like that in different locations, it is different. So we are giving the contribution from all those locations to the correlation of ISMR. That's all we are doing. It is entirely based on data, no dynamics. And the northward propagation doesn't come into play because here we are talking about only monthly mean. The northward propagation comes only on in subseasonal time scale. So I have not gone to a subseasonal time scale. Subseasonal time scale only it will come because I'm fixing this ZZAS mean. I'm trying to predict that mean. And how that mean is associated with all this D20 or SST or HC.
So your algorithm just gives the mean monthly picture.
Mean monthly picture, mean monthly
But
picture.
supposing that if in one particular year, a particular month has more number of such active and breaks, well, this
that will reflect in some changes in the monthly means. That will reflect. That is indirectly taken care of, but not in a very great detail, granular detail.
Thank you.
Mm-hmm.
Hello, sir. Hello, sir. So firstly, I wanted to ask, when we're talking about G-ENSO index, the SST that we are taking, is it the global SST?
Global SST.
Okay. So, for example, another question I wanted to ask is, since we were talking about the dependence of ENSO on ISMR is very less, that's why we're considering the global SST. So if for some other variability modes like the Atlantic Nino variability, the predictability for Atlantic Nino is extremely low. So do you think such a mode, such a climate mode, such as Atlantic Nino, will have an impact on ISMR, and will it be shown in the model that you have created?
Yes. Indeed, independently, Atlantic Minnow doesn't have a very strong correlation with it. Neither does IOD. Okay, but they still have some correlation, right? So which means that it has some impact. That variance explained is small, but every year it has some impact. Now, suppose I don't take that impact. There is some shift, some contribution to it, maybe 5%, 10%, maybe 20% some years. Okay, that contribution is there from these, and it varies from year to year. Now, if I don't take that contribution into account, then I will be missing out that, and I am correlating with that part only. So therefore, I'll never get the right ISMR signal. So even though these contributions are small, when I take the global picture, I'm getting the signal of ISMR, which is closer to observed. The observed signal will have that 5, 10, 20% of variation, which is coming from all these. And if I don't use that and only use Nino 3.5, that contribution acts like a noise, which is like a noise which should not taken into account, because that is now acts like a noise with respect to the observations, and therefore correlation goes down. That is like, so you have to take that small contribution also into the, as far as this is not, there is no way of doing it. Now we have a way of doing it. So the correlation will be poorer, and that is, so that means our skill will be bad. Every time we are missing something, and that, so in a way, this event-to-event variability, we are trying to include a little bit of that by using this particular predictor. So this is, and hopefully there may be an even better way to improve because this is the event-to-event variability is a kind of non-linearity. By using AI/ML model in a three-dimensional sense also, maybe we will be able to improve even further.
There's a question from the online audience from Moti Gupta. Sir, what would be your intuition why data-driven model do not suffer from model error and initial condition errors? Both could have model error, but dynamical models have physics-informed structure, while neural network have general function as approximation structure fitted using data. So why would neural network models perform better despite their inherent model error?
Okay, so the way I look at it is that neural network models, these are also essentially pattern recognition technique, non-linear pattern recognition technique. And and since it does not involve time integration, therefore, we develop a hierarchical temporal aggregation method, so that for each lead there is a different model which is trained. So we are guiding them to get the best pattern which is most correlated with to the ISMR. So that is why we have sort of this physics guided is important, and also avoiding the error growth by doing hierarchical aggregation method avoids the error growth problem. The dynamical models are limited by error growth problem, and because of model errors. And so even if there is error in the model, it is only limited by the model errors. So model errors means your pattern recognition techniques may be limited in some way, but because this is better than the linear UF kind of linear techniques, so it gives a better even in the data driven context. So earlier correlations, studies used either two-dimensional, either used is a sort of correlations with indices. Even if they had used artificial neural network technique, but they used with indices. Indices, if you correlate, even with neural network models, will not give you a good correlation, because you are again have partial correlation, partial relationship you are getting. So the important thing is to get the global contribution. And so that is one of the reason. And so when we do global contribution, even if some error in the neural network model is kind of is only that is limiting it, the other things are taken care of. That is why we are having a better correlation, I think. So that is, but of course it is not. I'm sure that there are some issues, and because as far as prediction is concerned, here it is the unlike the emulator model, where emulators has to keep the kinetic energy and energy of the system intact. So it should not decrease the structure, kinetic energy of the system. But here, since we are only talking about the prediction of a seasonal mean, so that problem is not there. If the prediction is good, it is useful. But when you come to a emulator model like the three-dimensional system, where we are making rollout predictions, there some of the kinetic energy in some of similar smaller scale structures may go down, and that may be a bigger limitation. So in seasonal prediction, we don't have that issue. But in weather prediction, that will be a bigger limitation, because the weathers are affected by the small scales. Now here the climate is affected largely by these larger scales, and so therefore I do have less of that problem.
Like if there are further questions, you can always discuss with Professor Goswami, who is here for 2 more days.